Everything you're about to see is performed in a proper environment by trained adults using proper safety gear. Please do not repeat this yourself. In this episode, we'll focus sunlight so intensely that paper starts burning in seconds. So does dry grass, dryer lint, and if you stick with us, even bunny poop. The story begins in 213 BC during the Second Punic War. The Carthaginian allied city of Syracuse was under siege by the Roman Republic. It was a brutal fight, but Syracuse had a secret weapon, a scientist and mathematician named Archimedes. Yes, the famous guy who jumped out of a bathtub shouting, "Eureka!" He designed giant mechanical claws that could flip Roman ships, and the legend says he even lined up mirrors to focus sunlight and set Roman boats on fire. What was that? If many mirrors reflect sunlight onto the same spot, the heat can get extremely intense. But what was that? A crystal that focuses light? Movie magic, right? In the real world, that clear piece of stone is a lens. I don't know if you like camping, but I bet you enjoy a good s'more. To make that, you need a campfire. And how would you start one? Use a lighter? A match? Strike flint on steel? Or go full primitive mode? Tell us in the comments. Today, let's use sunlight and a magnifying glass. It is sunny now, not hot, not humid, and a bit windy. I have a sheet of copy paper, dry leaves, some dryer lint, and as promised, a few bunny poop pellets. Hold the magnifying glass surface towards the sun. Move it back and forth, tilt it left and right, up and down, until you find the smallest, brightest spot of light. I see smoke. The paper is burning now. The dry leaves smoke instantly. This is why you never, ever look at the sun through a magnifying glass. Human eyes are far more delicate than paper or leaf. A single glance could leave a permanent blind spot. On fire now. Dryer lint also starts smoking right away. And the bunny poop? Immediately smoking because it's packed with dry fibers. Before we move on, I'd like to thank our volunteer who generously donated today's experimental supply, Mr. Lucky. It's easy to think sunlight reaches the Earth from different angles, but in reality, the sun and the Earth are so far apart that the sunlight hitting us is essentially parallel. So when a magnifying glass faces the sun, parallel rays go into the glass. That means we can use parallel laser beams to simulate sunlight. The middle beam passes through the center of the glass with no change, while the other two converge into one point. Move the laser source up and down. Do they all seem to hit the same spot? Let's stack the 3 video clips. All 9 beams converge into one point. That point is called the focal point, or the focus, and the line through the center is the optical axis. Movie magic, right? Use fingers to feel the magnifying glass. It's curved outward like part of a sphere. This is called a convex lens, more specifically a biconvex lens. If one side is flat, a plano-convex lens. Why can a lens bend light? Think back. How did we bend light? We used refraction. Light changes direction when it enters glass from air, and again when it exits from glass back into air. If one is good, two must be better. Oh, the focal points are different. Not all convex lenses are created equally. They have different focal lengths, which is the distance between the center of the lens and its focal point. By touching the surfaces of the two magnifying glasses, I can tell that the one with the longer focal length curves less. The more curvature a lens has, the more it bends light. A glass ball glows with quiet might, a tiny world that bends the light. Like a palantir from tales of old, a crystal full of secrets untold. But here's the wonder shining clear. What does light do inside a sphere? This is my precious glass ball.
Precious.
And a green laser pointer. Use the same movie trick, and here we go. They don't converge on the same focal point. Let's zoom in one more time. Not only do they fail to land together, but when the beams pass closer to the north and south poles, they intersect further away from the others. This phenomenon is called spherical aberration. In the next episodes, we'll focus on thin lenses with a clean focal point. This is called the thin lens approximation, and it helps us avoid complications caused by spherical aberration. Now you know what aberration is. We can talk about this popular optical demo kit. Lenses with different curvatures show different focal lengths. More curvature means a shorter focal length. What a lot of people don't realize is that when we move the beams further from the center, they no longer converge to a single focal point. That's the signature of aberration. These focal lengths are much shorter than the magnifying glasses from earlier, meaning stronger curvature, which brings more aberration. Notice the least curved lens produces the tightest bundle of beams. My glasses are full of fingerprints now. While I'm cleaning, why not also clean my nearsighted glasses? It feels different. The center is thinner, the opposite of a convex lens, a concave lens. Let's see what it does to the laser beams. Oops, wrong video. The beams diverge. They spread apart as they pass through the lens. But if we trace the beams backward, they appear to meet at a single point on the same side as the incoming parallel beams. That point is the virtual focal point, and the distance from the lens center to that point is the focal length. And just like before, if both sides curve inward, it's a biconcave lens. If one side is flat, it's a plano-concave lens. This is Dr. Walden from Graceful Science. Please like and subscribe if you can, and thanks for watching.